I want to investigate some tools that can be used with random signals. We need these tools to describe a number of different kinds of random signals. The random signal we're interested in largely at the moment will be noise. These same tools we've already applied to binary data streams. They may also be applied in some cases to analog information. An information signal like an audio signal or a video signal can be considered as a random signal, and you could even consider some sinusoids random if they have a random amplitude, a random frequency, or a random phase. Now, the primary characteristic of a random signal is you cannot write a specific equation for a signal like noise. So the best we can do is to look at its statistical properties, such as its probability distribution function, or more useful will be the probability density function. And these random signals will have statistical characteristics such as mean values and variance and even higher order moments, but what we will be mostly concerned with are mean values, that is the average value, and the variance, which is a description of how widely the random signal varies from its mean value. Let's review some of the statistical characteristics of a random signal. So let's consider a random signal, let's call it x of t, a function of time, and it varies in a random fashion. So we can find the mean or the average value. That's the bar across the top indicates the time average, and we will also consider this to be equal to the statistical average for this random signal. So this is the time or statistical average, or we will call it the mean value as well, with the bar across the top. The mean value is the average value, and it is also the DC value of the random signal. So if we have a signal that varies, but it has a DC offset value, this will give us the DC value. Second characteristic, if we take the average value and square it, so this is the mean value squared, this will be the DC power in the random signal. Third characteristic is if we first square the time signal and then take the time average, this is our definition of the mean of the square of the random signal. This is the total average power in the random signal. This is the way we've always found power in these notes. We take a time signal, square it, and then take the time average or the statistical average, whichever is more convenient. This gives us the total average power in the random signal. Fourth characteristic, if you take the signal, square the signal, then take the mean value, and then take the square root, this will be the root of the mean of the square. This is the RMS value of the random signal, the root mean square value. Fifth characteristic, the variance of this random signal is sigma x squared. This is a measure of how widely the signal varies from its mean value. This will give us the power in the time varying portion. We will call that the AC portion of the random signal. So a random signal has potentially a DC power and also an AC power. It's not sinusoidal, it's simply time varying, but for convenience sake, since we've called the mean value the DC portion of the signal. The time varying portion we will call the AC portion. So sigma squared is the power in the time varying part of the signal, and the square root of sigma squared is simply sigma. This is the RMS value of the time varying portion of the random signal, and statistically, if it's a Gaussian distributed signal, this would be the standard deviation. Here is a seventh characteristic of a random signal. If our random signal has zero mean, so it has an average value of 0, then if you square 0, you would get 0 DC power. And with 0 power in the DC, if there is no DC portion, so there's 0 DC power, all the power that is left is the power of the AC portion, sigma x squared. And this will be the total power in the random signal. And the variance, sigma x, will be the RMS value of the random signal. Now let's consider a random signal with a DC component and a time varying component. So our random signal x of t, this is the random signal x of t. It has a DC component, which is x with a bar across the top. This is the mean value of our random signal. And it also has a time varying component. This is x with the squiggle across the top. So our random signal has a DC component plus an AC component, and if you take the AC component and then you take its time average, that is going to be 0. This means it is a zero mean value. So the total average power is we found by taking this time signal squared. So inside the parentheses x plus x with the squiggle, we're squaring that and then taking the time average. So you complete this squaring operation, you get x bar squared plus the cross term. This should have a 2 right here. 2 times x bar times x squiggle. It doesn't matter because it's going to time average to 0. Plus x with the squiggle squared. And the time averaging is an integral process which we can break up into 3 integrals. So we're looking at x bar squared time averaged plus x bar times x with the squiggle time averaged, and again we need a value of 2 in there, plus x with the squiggle squared time averaged. Now if you look at this cross term, x with the squiggle across the top is the AC portion of the random signal. X with the bar across the top is a constant times a constant times a time varying portion with an average value of 0. So the constant times a constant simply scales the time varying version, and when you take the time average, it's still going to time average to 0. So 2 times x bar times x squiggle, and you take the time average of all of that, that's going to be equal to 0. So this cross term goes to 0, and what's left is the total power is equal to x bar squared time average. That's simply a constant x bar squared, which is the DC power, plus x with the squiggle, that's the AC portion squared and time averaged. That's the AC power, which is going to be equal to x bar squared plus the time average AC power is sigma x squared. This is the variance. Sigma x squared is the variance of the random signal, and it is the AC power in the random signal. So the total power is the DC power. This is the DC power plus the AC power. We can discover some information about a random signal from its autocorrelation function, and as we looked at with the random binary signal, the autocorrelation function of the random signal x of t is r sub x of tau. Tau is the time shift parameter, And this is by definition x of t multiplied by x of t minus tau, and then we take the time average. If we complete this for every possible value of t, we will have a function of tau, and this gives us the autocorrelation function. Properties of the autocorrelation, first of all, it has a maximum value at time shift tau equal to 0. So the absolute value of x of the autocorrelation of tau is always less than or equal to the value Rx at time tau equal to 0. And this is always a positive number. Always positive. That is the value at time tau equals 0. Now the autocorrelation may go negative during its course as tau changes from 0 to infinity, but the value at time tau equals 0 is always positive, and it will be the maximum value. Second property is the autocorrelation has even symmetry. Third property, the value of the autocorrelation at time shift tau equals 0. So this is at time shift tau equal to 0, is going to be x of t times x of t plus 0 and time averaged. Well, that's simply x squared of t time averaged. That is our definition of the total power. So the value of the autocorrelation at time shift tau equals 0 gives us the total power. If the time function, the random time function, has a periodic component, so it is a random signal plus a periodic signal, then the autocorrelation has a periodic component at the same period. If the average value of the of the time signal is not equal to 0, it has a DC component, and if the time signal has no periodic component, then if you look at the value of the autocorrelation as tau approaches infinity, that will be out near the tails of the autocorrelation, then that will give us the DC power in the random signals. So from the autocorrelation function, we can read the total power at time shift tau equal to 0, and we can read the DC power at time shift tau approaching infinity. And if you know the total power and the DC power, you subtract, you take total power minus DC power, and you are left with the AC power. If the random signal has a mean value of 0, and if it has no periodic component, then the autocorrelation will tail off towards 0. So this is just saying it has 0 DC power, which is what we have defined if it has a mean value of 0. See, if x of t averaged is equal to 0, then when you square this, it's at 0 as well. And the AC power, which is the variance sigma x squared, is equal to the value of the autocorrelation at time shift tau equal to 0 minus the value of the autocorrelation as tau approaches infinity. So this is the total power minus the DC power. Total power minus DC power. Now let's look at the power spectral density. We've looked at the spectrum using Fourier transform of a time signal. That gives us an amplitude spectrum. The power spectral density gives us the power in the signal distributed over the frequency scale. If a signal has a Fourier transform, then the power spectral density, which is S sub x, so this is the power spectral density of the random signal x of t, The power spectral density is a function of frequency, and it is simply the magnitude squared of the Fourier transform of the time function. So Fourier transform is in general a complex function. Sometimes it turns out to have an imaginary part of 0, but often it turns out to have some angle function as well. If we take the magnitude squared, which is going to be x of f times the complex conjugate of x, this will always give us the there it is written out. This will give us the magnitude squared. Now the units of the power spectral density is watts per hertz. So we're plotting watts on the vertical axis, and we're plotting frequency in hertz on the horizontal axis. Now it turns out the power spectral density and the time signal, the corresponding time signal do not form a one-to-one pair. So if you're given a power spectral density, you cannot tell precisely what the time signal was that produced that power spectral density. And to illustrate this, let me plot a sample power spectral density, and this is what I want the example power spectral density to look like. It's a pair of delta functions at a specific frequency, and they have a weight of 1/2. So we're given this. Oh, I'm sorry. Let's make it 1/4. That's even better. 1/4. So we are given this as the power spectral density for a particular signal. Now, you would think, well, when the spectrum is a pair of delta functions, that corresponds to a time signal, which is a cosine. Well, I submit to you that it also would be. See, this is the magnitude of the Fourier transform squared. It would also correspond to the power spectral density of a sine instead of a cosine. So see, this could be cosine of 2 pi fct, or could be sine of 2 pi fct, or it could be cosine of 2 pi fct minus some phase angle phi, and it doesn't really matter what the phase angle is. It could be this power spectral density could be any of these functions. So there's not a one-to-one correspondence between the power spectral density and the time signal. Now for a random signal, the power spectral density is the Fourier transform of the autocorrelation. So if we know the again, now I've got a see, we don't need a double x. Let's just keep that as a single x as a subscript. If we have the autocorrelation of a random signal, we take its Fourier transform. That will give us the power spectral density, and we use exactly the same definition of the Fourier transform. So the power spectral density is the Fourier transform of the autocorrelation of a random signal. Here are the properties of the power spectral density. The power spectral density is always positive. Remember, the power spectral density of a function is the magnitude squared of its Fourier transform, and the magnitude squared of something is always going to be positive. So the power spectral density never goes negative. It's always positive. It's symmetrical, and it's always real. Magnitude squared of any complex function is always going to be a real function. The average power in a random signal can be found by integrating the power spectral density over all frequency. So the power spectral density tells us how the power in the signal is distributed over frequency in such a way that if you want to know the average power or the total power, we could also call this the total power. Either one, that's P with the subscript X. That's the integration of the power spectral density over all frequency. If you want to know the power in a band of frequencies between F1 and F2, so we have a power spectral density as a function of frequency, and it looks like this. Just to give it a shape, I've tried to make it symmetrical, and we are looking in the band of frequencies between F1 and F2. It's we would find that power by integrating this area, but remember, for it's symmetrical, we also have to include the area between minus F1 and minus F2, and since it's symmetrical, the total area will be twice the area between F1 and F2. So power in a band of frequencies is found by integrating but from frequency F1 to F2, and since the power spectral density includes negative and positive frequencies and it's symmetrical, we can simply double that area to find the total power in this frequency band. Now, if you want to know the power at a specific frequency, then what you can do is, so we have, this is, I should have made this more symmetrical, I suppose. Here, you can watch me use the magic wand. If we want to know the power at a specific frequency F1, then we integrate. We're going to integrate. When you integrate, you have to integrate over a range of frequencies. So we can integrate from F1 just to the left of F1. This is going to be F1 minus epsilon, and we're going to integrate just to the right of F1. This is going to be F1 plus epsilon. So this is our range of integration, and then we're going to let this value of epsilon go to 0. Now, so we're integrating this area, doubling it because of the symmetry and the power spectral density. Now, when you let epsilon go to 0, this the power in this range of frequencies will go to 0 unless there is a delta function exactly at F1. So this integral would be as epsilon goes to 0. As epsilon goes to 0, this is going to go to 0. But if, on the other hand, we have this is the symmetric, we have this kind of a situation where there are a pair of delta functions, let's say, precisely at F1 and minus F1, and this has, I'm going to just call it S naught, and I'm going to call this S naught, and this is the power spectral density, and we want to find the power at this specific frequency. Then we're integrating over this range of area, and as epsilon goes to 0 again, now what this will go to is the area in this range of frequency. Even as epsilon goes to 0, you still have the area of these two delta functions. So this is going to integrate to an area or a total power of 2 times this value, S naught, whatever that is. So the DC power in a random signal is found by looking at the frequency range from minus epsilon to plus epsilon. That would be from just to the left of f equals 0 to just to the right of f equals 0, and then let epsilon go to 0. So the only way you will have DC power in a signal is if there is a delta function exactly at f equals 0. Now let's consider what happens when a random signal is passed through a linear system. So as always, if x of t is the input and x of t is a random signal, and that passes through a linear system with an impulse response lowercase h of t, then the output y of t, as always, is equal to the input x of t convolved with the impulse response h of t. And if we take the Fourier transform of the left-hand side, this is capital X of f, into the linear system, which is now described by its transfer function, h of f, capital H, uppercase H, which is the Fourier transform of the impulse response, h of t. Remember that the transfer function, capital H of f, is equal to the Fourier transform of the impulse response, lowercase h of t. And the spectrum of the output signal is equal to the spectrum of the input signal times the transfer function. And this is a very useful relationship. And it's sometimes it's a lot easier to work out this multiplication than it is to work out this convolution. So you can see the advantage of using the Fourier transform and finding the transfer function and using multiplication instead of convolution. Now, if we want to know the power spectral density of this output, we want to know the power spectral density of the output y, which is y of t. The power spectral density of y is equal to the magnitude squared of its Fourier transform. So we take capital Y of f, magnitude squared, and that will give us the power spectral density. So the Fourier transform, uppercase y of f, is equal to x of f times uppercase the transfer function, uppercase h of f. So we make this substitution. So we have uppercase x of f times uppercase h of f. Then we're taking the magnitude squared, and it works out that you can take the magnitude squared of these individually and then multiply them together, and you'll get the same result. So work this out with general complex numbers, and you'll see that it's true. Now, we've already defined the magnitude squared of the capital X of f. That's simply the power spectral density of the function x. So the power spectral density of the output from a linear system is equal to the power spectral density of the input to the linear system multiplied by the magnitude squared of the transfer function. Now this is a little bit of a different different result than we are accustomed to. We are accustomed to the Fourier transform of the output is equal to the Fourier transform of the input times the transfer function, but the power spectral density of the output is equal to the power spectral density of the input times the magnitude squared of the transfer function. I've posted some assignments to reinforce these observations and definitions, and it's pretty straightforward to work these out. First of all, we're dealing with an autocorrelation. A certain random signal has this autocorrelation function. See, here is the zero line. It's got this symmetrical shape, which is what an autocorrelation will have. It's got its highest value at tau equals 0. So this is time shift tau along the horizontal axis. So its highest value, and also see the value of the autocorrelation at x at time shift tau equal to 0 is this value right there. So you can find this value. And we also know as tau gets increasingly large, it settles in on a particular value. So the autocorrelation of x at tau approaching infinity is given by this value. So we know, the total power, the DC power. Total power minus DC power will give you the AC power. So if this curve, let's say this curve takes a basic exponential shape. So if you were to write a function for, let's just say this is just the part of the curve going to the left. I'm sorry, to the right of tau equals 0. It's got the mean value plus some kind of constant times e to the minus tau, since we're a function of tau, divided by some kind of time constant tau naught. So that would describe this curve. You can fill in the values for this. The DC offset value is easy to find. The additional height of this decaying exponential is easy to find, and the time constant, or this time constant tau naught, is easy to find. I've just given it this name, but remember that with these decaying exponentials, the decaying exponential reaches its final value in 5 times the time constant, and it looks like it seems reasonable to me that between tau equals 0 and tau equals 1, it has reached its final value. So you can take this time constant to be, this would be 5, see, 1, 2, 3, 4, 5 times, so this is tau naught, 2 tau naught, 3, 4, this is 5 times tau naught. So you can find a numerical value for tau naught. So this is essentially the curve, the equation for this curve, and it would be symmetrical, so you could find a corresponding equation for the left hand side. And now if you want to know the power spectral density of the random signal is always going to be the Fourier transform of the autocorrelation of this autocorrelation function. You can write an equation for the autocorrelation. You can find the Fourier transform for this autocorrelation, so you can sketch the corresponding power spectral density. And now what I want you to do, after you've sketched this power spectral density, and I'll let you work out what the shape of that looks like, you can integrate this power spectral density and find the total power in the signal, and the value you get from this integration needs to match the value you got from the autocorrelation. Okay. This is the power spectral density of a certain random signal. It has some various shapes here, and it's also got some delta functions as well, and you know the areas underneath these delta functions. First question is, what is the total power in the signal? Well, the total power is going to be the integral from minus infinity to plus infinity of the power spectral density integrated with respect to f. See, that's going to give you the total power. So you simply have to find the area underneath this entire function. So you have the area under this little triangle plus the area under this delta function plus the area under this house shape plus the area under this delta function plus the area under the delta function plus the area under this little triangle. Now I don't think it's necessary to set up integrations and work out the integrals, because you can find the area underneath these geometric shapes pretty easy. What is the DC power in the signal? Well, the DC power is you integrate from minus epsilon to plus epsilon. You integrate the power spectral density as epsilon goes toward 0. That's going to give you the DC power. So you're integrating this tiny little region between minus epsilon to plus epsilon, and when you do that integration, you will get the area underneath this delta function, but the area underneath this house shape is going to go to 0 because the width is going to 0, so you're left with simply the area underneath the delta function. What is the AC, or the time varying power in the signal? Well, total power is equal to DC power plus AC power. So AC power is equal to total power minus DC power. What is the power and the bandwidth from between 6 and 8 hertz? Well, you've got you're integrating the area between 6 and 8 hertz, but don't forget you've got the corresponding area between minus 6 and minus 8 as well. So that's simply the area under these two little triangles. What is the power at frequency f equals 4? Well, here you're integrating the tiny region between 4 minus epsilon to 4 plus epsilon. So you're integrating the region right at 4 hertz. So you've got this delta function, but don't forget you've also got a delta function over here. So that gives you the power, the total power at frequency f equals 4. What is the power at frequency f equals 7? Well, that would be, see, you're taking the value at 7 and you're integrating a tiny little region each side. So this would be this little area. But then remember, as epsilon goes to 0, the width of this region goes to 0, and so you're taking whatever this height is and multiplying by 0, and anything multiplied by 0 is 0. So that's going to work out to be 0. Even if when you double 0 is still 0. Now let's look at problem number 45. We've got a random signal m of t that we have described with its power spectral density. That's this signal that has a certain power spectral density that goes through this linear system, h with the subscript c, which has a transfer function given by this function, and then the output from this linear system is added to noise, and then the sum of the signal plus the noise goes into this transfer function, or this linear system, which is described by the second transfer function, and then we have the output signal. So we can consider the signal from input to output, and so if we were to just draw the signal path, let's call it that, we've got m of t into hc of t, that's its impulse response, into h lowercase hd of t, this is the second impulse response, and out y of t, we would have s, this is y of t. Now we know the signal m of t by its power spectral density, which is given to us with this equation. We know this linear system by its transfer function, which is given by this second equation, capital HC of f. We know the second linear system by its transfer function, and we will know the the power spectral density of the output. Okay, so this gives us the result of the signal path. Let me get another piece of paper, and we can we know that the power spectral density of the output signal is going to be, first we have the power spectral density of the input signal times the magnitude squared of the first transfer function. Okay, so that gives us the power spectral density input to the second one, and now the output will be this power spectral density times the second transfer function magnitude squared, and so this will give us the power spectral density of the output signal. So you have here the the power spectral density of the input signal. You can find the magnitude squared of the first linear system. Now this okay, let's see. This is going to be we take the magnitude squared of this transfer function. That's going to be the numerator squared divided by the numerator magnitude squared divided by the denominator magnitude squared. Magnitude squared of this complex value is going to be the real part squared plus the imaginary part squared. Now the imaginary part is simply f. We have the real part plus j times the imaginary part. It's not j times f, it's simply f. So this is f squared. So this is the magnitude squared of this transfer function. And then we take the magnitude squared of the second transfer function. Got the magnitude squared of this numerator, which is going to be the real part squared plus the imaginary part squared divided by the denominator magnitude squared. And then that's multiplied by this rectangle squared, but a rectangle squared is easy to do. It's 0 outside the limits of the rectangle, and inside the limits of the rectangle it's simply 1 squared, so you can figure that out. So the power spectral density of the output signal is going to be the power spectral density of the input, which is beta times this rectangle, beta times the rectangle f over 8,000, that's this, times the magnitude squared of the first transfer function, times the magnitude squared of the second transfer function, and that gives this gives the magnitude, the power spectral density of this output signal, and then you can do the math, the simplifications, and you'll notice that so the total output signal power, that's S0 here, is going to be the integral from minus infinity to plus infinity of f s sub y of f df which is it's going to be the integral, and now the limits are set by the rectangle functions. We've got a pair of rectangle functions, so you'll have to see which one sets the limits. This rectangle is more narrow than this rectangle squared. Rectangle times a rectangle. That's still, you multiply these two together, you still have a value of 1 between the appropriate frequency limits. I'll let you figure those out. So this will evaluate to a number, and it will involve beta, and it will involve a particular band of frequencies. So that's the signal path. The noise path is going to be the noise. See, the noise is added to the signal, so the noise goes through the second linear system. This is of T, because this is the impulse response, and then out comes, I'm going to call it noise out time, and noise, power spectral density of the output noise with respect to F is going to be the power spectral density of the input noise with respect to F times the magnitude squared, capital H D of F. And the power spectral density of the noise is simply a constant value. The magnitude squared of the transfer function is given by this equation. So you can find the noise power, which would be equal to the integral from minus infinity to infinity, the power spectral density of the noise, which is a constant 10 to the minus 8, 10 to the minus 8, times the magnitude squared of this transfer function, which is 4,000 squared plus F squared divided by 4,000 squared times a rect squared F divided by 16,000 dF. So this rectangle squared will set the limits of integration. So you can easily evaluate this integral once you've figured out what the limits of integration are. Completing this integration is it's pretty straightforward calculus. I think you'll be able to figure that out. And this will evaluate to a value, to a number. Then what you can do is set the signal out to noise out. So the result from this calculation, which will be a function of beta and a certain frequency band, frequency range. We'll see this is signal out to noise out, and you calculate the noise out. Set the signal to noise ratio equal to 55 decibels. So this is going to be this would be equal to 10 to the power 5.5, 55 decibels. I believe that's right. You can work at that. I think that's right. And then solve for the corresponding value of beta. Okay, that's how you work this first this first part, and I've tried to outline it. There's some of the details you have to work out, but think about what the signal is going through and what the noise is going through, and you should be able to work that out. The signal power at the input of the receiver, that would be the see, we've got the power spectral density of the message signal going in to this first linear system, multiplied by the transfer function magnitude squared, and then integrate the term at that point, which just would be this term and that term. You integrate, and then you will find the total power at the input. And see, in this process, you also have to find the total power at the output. So you'll work for using this value of beta. You can calculate those two values. Okay, this is a little bit more involved, so but that's a good exercise for you to go through, I think. And I think this is all we really want to say about about noise signals and transfer functions.